Director of Technical Training, and welcome to the Grundfos Technical Institute presentation on Advanced Green Building Design this morning. Our speaker today is Kevin Anderson, Pump Training Specialist for Grundfos. Our session this morning will last approximately 45 minutes to an hour. Please enter any questions in the box in the lower right corner of your screen. With that, we'll begin our webinar presentation with Kevin.
So good morning. So what we're going to discuss today are green building design with multiple chillers and boilers, and some of the best practices and some considerations that we want to think about in designing for green building applications. So upon the completion of the training, we should be able to identify the differences between open and closed loop hydronic water systems, understand some of the alternate primary, secondary pipe systems, explain some of the importance of where the sensors are located in hydronic systems, and understand the importance of a life cycle cost analysis for hydronic systems, review some of the different piping methods, and also understand how variable volume, variable speed pumping influences pipe sizing. So for this application, the piping schemes we're going to look at is for one of our largest buildings. In this example, would be for like a larger hospital. In the hospital building, it'll consist of like office and patient areas. The patient areas open 24 hours a day. The office areas would be a little bit different from 8 to 5 p.m. Monday through Friday. The building characteristics for this application is a 4-story building with a basement, roughly about 140,000 square feet per floor, and then just built under a standard construction. Now, some of the differences for the standalone operation, it's similar to smaller buildings. The main thing you'll look at is that there would be availability for larger pumps, as well as some additional applications that wouldn't normally present themselves in smaller buildings. Now, when there are multiple buildings, such as a large complex with a central plant, the multiple buildings are then served from a single heating and cooling source that's located in the central plant. And then the hot and chilled water are both distributed to each of the buildings through the piping loops. Now, ideally, the central plant should be located to the central to all the buildings, but that rarely happens. Often the design for the architecture would be different that wouldn't make that be able to happen. Now, the farther that the chiller plant is from the most distant building, the more expensive it is going to be to both build and operate the heating and cooling system for the plant. So we'll look at some of the similarities and differences if we're using a campus complex with a central plant. So all of the previous examples for piping for a single building could exist, but then some of the differences is that the pumps could be larger. The distribution piping can be different depending on the design. And as mentioned earlier, the location of the central plant is very critical to the design for the system. And then multiple central plants may be tied together if needed for these types of systems. So let's explore the next level of the pump application and looking at the idea of the complex central plant. So there's two broad classifications for the piping systems with some of the variations for these. The first is a closed loop systems, which would include chilled water systems as well as hot water systems. And then the second would be open loop systems, which could consist of condenser water systems, domestic hot water recirculation, as well as domestic pressure boosting could also be included in that. The diagram we're showing here is for a two-pipe direct return system. Some of the advantages of a two-pipe direct return is it lowers the return water temperatures and increases the boiler efficiency. It minimizes the flow to the coils, so it saves the pumping horsepower. It decreases the secondary flow, so it also saves on pumping horsepower. And then it reduces the boilers that are online, which also helps save energy. Also, it helps boiler performance is increased, saving some of the operational costs, as well as the ease of the system operation by reducing some of the operational issues that could exist. And also it helps save energy by making the system more economical to run. And it is the preferred piping method because it provides familiarity to most system operators. So we can see here listed, we have on the left side of the system, we have our primary pumps. Then we have our secondary pumps. On the bottom we have our main common pipe with our expansion tank as well as our air separator on a return. And then we do have these pumps controlled by a multiple pump controller. Now some of the applications that are used for the two-pipe direct return, it's the basics for most chilled hot water systems, and they can be found in some of the larger, smaller as well as medium-sized buildings, from low to high-rise systems, single or multiple buildings. And then there's also less operation flexibility since each of the building sees the same supply temperature to the application as well. Now, when designing a two-pipe direct return system, there's three things that need to be considered for these, so some of the piping tips involved. The first is that it does use a proper common pipe design. And then it's got one tank that's located at the point of no pressure change. Also for the warmest water. And then it utilizes air control as well as air relief for the system, for the warmest water for the application, and also the highest pressure drop throughout the system. And then it utilizes two-way valves that are located downstream of the coils. And we'll talk about some of these details a little bit later in this section. Now, two-pipe systems, they do have both advantages as well as disadvantages. One of the main advantages are the simplicity of the design and the operation, and then the first cost effective, so it's more effective for first cost installation costs, and they're efficient to operate. Now, some of the disadvantages would include the head requirement, because often there could be overpressurization of the zones that are located near the central plant. There could also be some balancing challenges to balancing the system. Also, the systems are thermally linked, which means that all of the applications are subjected to the same water temperature supply. Now, another type of a design is a primary, secondary, tertiary design. And it has a few important variations in this type of a design. As you can see here, we've added a third set of pumps as well as additional common pipes for each of the zones or buildings. Now, multiple secondary and tertiary pumps may be used. A single pump is just shown here due to the space that's allowed for this drawing, so it doesn't have quite all of the same controls that you'd normally see, again, based for the space for the design. So some of the main places where we'd use this type of a piping, some of the common applications could include multiple building campuses, campuses with application diversity to them, could be for campuses that have long piping runs, could also be campuses with multiple production plants, as well as campuses that have large elevation changes in the systems as well. And also campuses with varying heights for the buildings. Now, one main difference with the tertiary loop piping it's not all the zones or building are operating the same. So the tertiary pipe systems provide kind of the ultimate flexibility for the design and the operation of the individual zones or the buildings. So the common pipe hydraulically isolate each system. So at no time is an individual building dependent on its neighbor. Then the individual supply or water temperatures can then be achieved and maintained, and then the head required for each pump for each building is also independent rather than running on common pumps. And then the pumps for the individual buildings are then calculated as if no other building is involved in the system. Then the secondary pumps are then relieved of the head required to serve the entire individual building. And then the secondary pumps are also selected just to overcome the friction loss in the distribution piping to and from the central plant, as opposed to also overcome all the head within the building. So then the excess head required to pump to the building due to the large loads or high resistance is not imposed up or downstream of the building. And then the tertiary pumps are selected for the building load only. So they tend to be a lower horsepower, which is really an ideal application for the Magna 3 and some of the opportunities there. Now, when primary, secondary, or tertiary designs could also be designed with plate heat exchangers. So the plate heat exchangers replace the secondary, tertiary common pipe. So if we look at the design from earlier, the principle for the primary secondary piping means that the changes in pressure or flow in the primary will not cause changes in the pressure or flow of the secondary and vice versa. So the plate heat exchanger represents kind of the perfect common pipe. So at no time can the flow or pressure change on one side of the heat exchanger affect the flow or pressure on the other side. So it's just used for the a heat transfer device only. So shown here is kind of a simplified schematic showing a plate heat exchanger in place of the common pipe. So some of the accurate piping details are shown more diversified in some of the later slides. So to talk a little bit about what a gasketed plate heat exchanger is, or a plate frame heat exchanger. A plate heat exchanger is just a device that just transfers the BTUs from a source and a load without the fluids actually coming in contact with each other. So the plate heat exchanger, it's a compact device which can be located either indoors or outdoors and insulated or not, depending on the application. This is accomplished through flow patterns between a series of different plates, usually made out of a stainless steel, and so it's patterned in such a way that the flow is in opposite directions every other plate. So as we can see here, from the load and to the load from heating, or from the load to the source for cooling, and reverse depending on the application. So it's patterned in such a way, again, so that this flow provides a maximum heat transfer from the source to the load. So it's essentially known as a counterflow. Now there's two important factors when sizing a plate heat exchanger, and that's the pressure drop and the approach temperature. The approach temperature is the temperature difference between the source fluid and the fluid delivered to the load. So a very close approach of around 2 degrees Fahrenheit can then be achieved without a large pressure drop throughout the system. So a close approach and low pressure drop doesn't come free. Actually, it's kind of an inverse relationship. The closer the approach and the lower the pressure drop, the more expensive the heat exchanger unit is. So the plier of this type of a device, they'll gladly demonstrate the cost effectiveness of the selection for the system. Also, the plate heat exchangers vary in their size, shape, pattern, which also impacts the selection process. And the plates are also available in a variety of different materials to meet different application needs, including either double-walled for potable water type applications. So a plate heat exchanger acts as a pressure isolator. So if you consider a multiple building campus with a central plant, there could be blocks or miles from the first takeoff all the way out to the farther zone. So the near building may be a one-story multi-office building, which requires about 20 feet of head to serve the highest valve and coil, where further downstream could be a 25-story hospital structure requiring 90 feet of head to serve its farthest load. Well, why should the multi-office building and all of the others be subjected to the pressure that's required to serve the hospital downstream? Well, really they shouldn't, and that's where the plate heat exchanger comes in, because it eliminates that additional head requirement in the early buildings. So once again, this is kind of a simplified connection of the plate heat exchanger to show for this application. Now, a couple of piping tips when using the plate heat exchangers in the primary, secondary, tertiary systems. When the heat exchanger is used, additional tanks and air separator devices must be added to the tertiary loops, and also controls for the secondary and tertiary systems would then be independent of the main systems. Now, again, there's both advantages and disadvantages to the primary, tertiary, secondary, tertiary systems as well. So some of the advantages, as we mentioned earlier, there's now a hydraulic isolation of the different pressured areas. Also, there's a thermal isolation for the independent temperature operation for each system. Also, there's a horsepower reduction now for less horsepower required for large main pumps by sectioning off each pump. There's also operational cost savings now for reduced energy through those smaller loads, as well as there's a much greater system performance optimization in this type of a design. Now, some of the disadvantages is there will be additional piping costs. There will be additional control valves that are needed for the application. There's going to be an additional first cost for the additional pumps, heat exchangers, and design. And then also there's could be an over-pressurization of some of the near zones if you're not using a plate heat exchanger, which would also then, with this type of a system, would result in more pumps being needed for the system. So other piping configurations to be considered, such as the chiller piping. This type of piping is open piped, which requires some additional design considerations. The first is the condenser water systems are found with or without an economizer, depending on the climate conditions. So we're going to look at both condenser water piping as well as condenser water piping with an economizer in the system. So with condenser water systems, there's pumps that are required to circulate the water from the chiller condenser to the cooling tower and back. When it's piped in an open system, a filter or a sediment separator is often used. Now, in areas where there's excessive dirt or debris present, then a plate heat exchanger with an additional pump is often used. So as we can see in this diagram here, we have the tower on the left, and then we have it with the optional plate heat exchanger in the pump, and then the sediment separator for the system. So that's going to and from our condenser unit, and on the right side is actually serving our load with our evaporator, with our primary pumps, secondary pumps, into our system, and then expansion and air tank returning back to the system. Now, the addition of an economizer loop can also add additional pumps to the systems. So as shown here, now we have our economizer loop in the bottom with our heat exchangers. Now, a water-cooled chiller requires that there be a heat rejecting piece of equipment that's located outdoors. So in this case, it's the cooling tower. And again, this piece of equipment is connected to the chiller's condenser, creating the condenser water loop. And then two additional piping loops exist inside the building then to distribute the chilled water to the space loads such as the coils. One of these loops is the primary loop, and then the other is the secondary loop. And then the details of this piping configuration, it's important so that we can see the difference compared to the piping systems that then incorporate the water economizer. So with the water economizer, an additional piping loop is then added to the systems that's shown here in black. If we ignore this new loop, the piping is matching the previous slide. Now the system is not altered when the operation temperatures of the hot and cooling water demand is high, and the cooling chiller and the cooling tower operate. The economizer is then ignored. Now, when outside air temperatures are temperate, so below about 50 degrees dry bulb and about 45 degrees wet bulb, the work done by the chiller can be decreased as a result of the free cooling, because the cooling tower's evaporative cooling can then achieve a low enough water temperature to reduce the entering water temperature into the chiller. Now, this is considered a water economizer. In this scenario, the two-way control valve closes, which then is directing the water through the heat exchanger, cooling the return water temperature going to the chiller. And this is represented by the purple piping. This ultimately allows the chiller to work less, and therefore it decreases the energy consumption of the system. Now, there are different types of economizer piping configurations, and this configuration is referred to as a water pre-cooling. Now, the advantages of this configuration is that it protects the equipment from the open water condenser loop, and for a pump manufacturer, it requires additional pump. Now that we understand a water economizer and a little bit of how that impacts the piping configuration, we can discuss a little bit of the implication of this with the ASHRAE standard 90.1. Now, the fact that the economizer is required, it's straightforward in this application, but the maximum pressure drop requirements need a little bit of additional explanation. So the head, or the pressure drop that it's associated with the heat exchanger, must not exceed 15 feet of head of water, or a secondary loop must be created in the system per 90.1. So the purpose of the secondary loop is to ensure that the pressure drop is not seen by the pump during the normal cooling operation. Now, the addition of a secondary loop for a configuration of piping, as discussed earlier, means that the addition of a pump to the loop that connects the heat exchanger to the chilled water return. So then the addition of this pump allows the heat exchanger loop pressure for that drop to be disregarded in the calculation to the size of the chilled water pumps used in the normal operation. So this is important to limit the potential energy losses of the system configuration while taking advantage of the energy savings of the economizer cycle. So we're going to talk a moment about some of the best practice for life cycle costs and in that part of the design. So the LCC just stands for the life cycle cost for the system. So what is the life cycle cost? And then what are some of the key cost factors that we'll be discussing? And then what are some of the energy savings that can be generated when we consider the total life cycle cost of the system? So the first thing that comes to mind generally for most people is the initial cost of the pumping equipment. But really, is that all that needs to be considered in the cost of a pumping system? If we think about it, the initial costs really are just kind of the tip of the iceberg when it comes to the total cost of the systems. But really, there's a lot of other hidden costs in the system. There could be the installation costs and the commissioning, the energy costs, the operating costs, the maintenance costs, downtime, environmental costs, as well as the decommissioning and disposal costs. And these are the hidden costs that are really involved when we're calculating the true life cycle cost of a pumping system. So in most cases, the life cycle cost equation is very simplified for applications. Life cycle costs in the simplified method, it's considering what the energy costs are, the initial equipment costs, and then the maintenance and repair costs. Whereas many of the other costs that are included in the system, such as operating costs, downtime, environmental costs, and decommissionings are all the same for most systems, where the energy costs, initial costs, maintenance, and repair are probably the main three items that can be that much different depending on the system. So in reality, we need kind of a breakdown to look at the energy costs to get a real true picture of the life cycle cost for the system. So the energy cost is more than just the cost of power. Although that's significant, it's also how we use that power that's also important. As we discussed in some earlier applications, we have to consider the energy profile of the building as well as what the actual energy cost is. So not just the worst case scenario, but really what's the true load profile for the building. Then we also have to think about the efficiency of the pump and the motor, as well as if a variable speed drive is used in the application. Then we also have to consider the control method that's used for operating and running the pump. And then we also have to consider the number of the pumps that are utilized in the system. So really a summation of all these different factors will provide us with a true life cycle cost picture for the application. So let's continue by kind of putting three price tags onto the new pumps for our system. So the things that we need to think about are the initial costs. So that's the cost of the pumps, sensors, controls, motors. Then we also have to think about the maintenance costs of the pumps and the related components to those components. And then, of course, we also have to think about the energy costs, which includes the power, the load profile factors, and et cetera, which we've just discussed. So if we think about these three main items, the initial costs, maintenance costs, and energy costs, which order would you see that these three would be in? So I got a quick poll that I put up here to kind of get an idea of where you see these factors would be in. So if you go ahead and take a moment just to answer this poll. Okay, so we can see we got kind of a mixed group as far as which of the three we have. So we got kind of an even load for all three. So let's take a look at this. So actually, when we're talking about a variable speed type of a system, we're adding the controls and the variable speed drive, the initial costs equate to about 10% of the cost for the system. And then the maintenance costs are reduced to about 5% because, again, because of the variable speed drive and the proper control methods, especially if we're using a Magna 3 pump, are then reduced for this system. And really, the energy costs are the largest portion. So if we look at these, they're not all three equal. So when we look at the initial costs, if we guess 10%, well, that's reasonable if we're using a Magna 3 installation because, again, it includes the pump, the motor, variable speed drive, the sensing elements, as well as the controller. Then also when we look at the maintenance, well, now that's also reduced because, again, the efficiency and the wet rotor design of the pump, so the maintenance costs are also reduced. And normally I don't think we'd pick 85%. So again, it may not be free for many applications, but for a lot of other pumps, there wouldn't be as much of an advantage as there are for the Magna 3. So then the 85% price tag for our energy costs, this is really where the Magna 3 shines versus the competition, because of all the features of the Magna 3, as we discussed earlier. The operating cost for the Magna 3 is the lowest in the industry when it comes to the pumping costs and the power considerations for the pump. So now going forward with some of our best practice design, we're going to look at a case study for a 20-story hotel building. It has 35 air handlers, 450 fan coils. It has 7,000 operating hours per year cooling load. It has a main pump serving 900 gallons per minute at 62 feet of head using a 20 horsepower pump. And it's got a cost of electricity based on about 10 cents per kilowatt. And then it's based on a load profile for a 20-year payback. So now words are one thing, so let's go through an example retrofitting of an existing hotel. And what we're going to do is we're going to examine the life cycle cost, comparing it with a number of different pumps, control methodologies, and then the pump flow and speed characteristics for the system. So the first one that we're going to look at is just a single pump for this application running on a constant speed, constant flow. The second consideration we're going to look at is, again, a single pump, but it's going to be operating at a constant speed, but using a variable flow control. And then the third method that we're going to look at is a single pump operating with variable speed and variable flow. And then the fourth selection we're going to look at is using parallel pumps. They're going to be sequenced, also using variable speed and variable flow operating controls. So we're going to look at first is looking at the payback curves for our 4 different examples. So the first is our single pump operating at a single constant speed at a constant flow. And then the second is our single pump operating at a constant speed in a variable flow mode. Then the third selection is going to be the single pump operating variable speed in a variable flow. And the fourth is our 2 sequence parallel pumps operating variable speed and variable flow. So where these curves intersect then determines what our payback period is for each of the pump. So the payback period is less than 1 year for either of the two Magna 3 options. So if we go either option 3 or option 4. Now the parallel Magna 3 pumps not only offer a 21% energy savings over a single, but also offer some security of a second pump just in case. So if we look at these and actually look at them from a life cycle cost analysis for the 4 examples over a 20-year period, and we'll look at the product, which again in a good system is the life expectancy for the system, we can see that the first single pump is operating. We can see that the first single pump operating at a constant speed, constant flow, its initial cost is $1,948. Our maintenance costs are $779 for a total energy cost over the 20-year period of $294,545, which give us a total cost for the system, or a total life cycle cost for this application, of $297,273. Where if we look at the single pump in a variable flow, well then our initial cost and our maintenance costs would be the same, but we would get a reduction in energy costs for when we're operating at the lower flows of $230,309 for a total life cycle cost of $233,036. Now when we look at the initial cost for the Magna 3, although our initial cost would be higher for the pump at $6,883, even if maintenance costs were the same, which again they wouldn't be for a Magna 3, but now our energy costs are now reduced to $157,200 for a total life cycle cost of $164,862. Well then if we do the two pumps in parallel, now our initial cost would be $7,922. Our maintenance costs would go up a little bit due to the additional pumps required of the systems, but now our energy costs have been reduced to $91,418 for a total life cycle cost of $100,379. So now if we look at the difference between the single constant speed, constant volume pump versus the parallel variable speed, variable volume Magna 3, we can see that there's 1/3 of the operating cost over the life cycle of the pump. This is where we see really the true life cycle cost analysis difference. So we can see over a 66% energy savings in the cost of the systems. So here's another example using a shorter life cycle cost system, and this is just based on a 7-year life cycle cost analysis. So if it's based on an example that's published from an article in pumpschool.com, you'll notice that here the ratios are a little bit different from our previous example, because in a 7-year calculation, the initial purchase price is a little bit larger, again, because it's a fixed value based on a shorter term. But again, over a 20-year term, the energy costs become even larger portion of the pie, as we saw in our previous example. So really, the recipe for energy savings really is in your hand. First, main thing we want to do in our system is we want to keep the flow down as much as possible. And we want to be able to use Magna 3 pumps in the systems. And then really control is really vital to the system. When you can use a programmable Magna 3 pump, then you can control what type of operation you want to run the system. And then also we always want to make sure that we use a life cycle cost analysis for the total cost of the system, not just a first cost analysis for the system. And again, whenever possible, specify the Magna 3 pumps for the systems because of the additional energy savings. So really, you want to demand more from your system. The Magna 3 pumps plus the life cycle costing for the system really gives you all the tools that you need to really help design an energy efficient system and reduce the life cycle cost for the system. And that's the total recipe for energy savings: is proper design, proper products used in the right application.